Right, this now our simulation video for the microcontroller control. As you can see, I have my microcontroller there. This is a PIC microcontroller. You just look at the general outlook there. The only difference to the one that I have used myself, the AVR, the ATmega 8, is that this on the simulation diagram that I've used, they are here, and there's no crystal here, and these relays are not there. Let me show you quickly. This is the circuit that I've used on my inverter. This is an ATmega 8, though 32 pin, because it's a used board. Sorry, it is a board that was from another machine, so I've used that board for my microcontroller circuit. As we discussed in my previous video, is that simulating using this part here is the simulation is very slow, and you won't see much of what is happening because the response is slow. Right, so let's use the PIC version of this PIC 16F876A. I'm sure you can actually take this code, the code that I've used, this one here, and actually load it to a PIC 16F886, and it will still work, and similar PIC will actually accept that code. I've done it before on my alarms, that I've used a PIC 16F716 with the code of a PIC 16F819. Right, so let's go on. Right, let's run the simulation. This is the on-off switch, and this is the off switch. I said on-off, but it's actually an on switch. Okay, and this is the off switch. Right, here is the display. This LED indicates the state when the inverter is off, or the mode in which it is when it's off, this D3. Right, and here is the transistor to drive the fan. That is the transistor to drive the buzzer, and here transistor to drive the on-off relay, and here the transistor to drive the output AC relay. Right, and then here is the setup when you have chosen to run the 4013 IC using the microcontroller output, and the microcontroller will output a 100 Hz square wave signal with the either low pulses or high pulses. Explain that later when we are discussing about this one in this video. Right, so let's run the simulation. I've already loaded the code to my simulation as is. Okay, you can see that this LED is flickering like that. The default is actually the mode for solar powered inverter. That's how it does. And then if you want to change the mode, you press this on off button here long, with the off button long, and then the flickering will change to slower. It will change to slower. As you can see, now it has changed. It's now a slow flickering. Now let's go for the solar default mode. Let's go for the solar default mode. Right, it has gone solar default mode. Right, to start or switching on the inverter, I go switch on. You check these LEDs, they will change, and the relays here, they will also be activated. Right, let me switch it on. Check the LEDs, they are now flickering up like that, going up like that, and then here on the LEDs they will come on. Right, it's now running. Okay, and check this one to come on, and the relay right, operated, and the LED coming on. So the on relay has come on, the AC output relay has come on, and even the signals are now running. And this is the signal that you get at the output, the modified square wave or the modified sine wave. You add the C and the D channel. Here I can't add A and B because I've tapped the output from the microcontroller. This is the output from the microcontroller. These are low pulses, and the high pulses are actually the inverted part of this. If I invert that, this is what I mean by high pulses. High pulses is a smaller pulse width going high, meaning a duty cycle, small duty cycle. But what I'm inputting into the 4013 IC is this signal here, low pulses, high duty cycle. Right, so the inverter is running and you have that signal here. Let me just show you quickly what I mean. Okay, the D is here, the D is here, right? So it's A, B, C, D. You compare C and D, you see that difference here, that difference here. That difference matters. This is the gap that you see here. That's the gap that you see here. That's the gap, the dead time. So the dead time is critical on the signal. So this part here is the dead time. Okay, peak is running like that. And if I want to turn off the inverter, I just push to make a momentary setup. That's a push to make button. Right, put it on again to start to run. It will wait for some seconds for things to settle, and then the on relay comes on, and then after some seconds, for 3 seconds, the AC output relay comes on. But here it already shows you that the inverter is on, it's running, right? And then it comes on. Now okay, if I change the temperature, transistor turns on. You can see this one has gone high, and then if I go back, it will run for some seconds. I think I've made it 1 minute, and then it goes off. And if the temperature is too high, and like the resistance of this thermistor is gone very, very low, the inverter will actually stop running and gives you an alarm after 3 seconds. Like that, you see that it will actually stop running and give you an alarm. Right, after some 3 seconds, right, you see it has actually stopped running, and the alarm is this LED flickering alternative, this one and that one. That's the alarm condition. That's for temperature and also for the voltage. So let me go back. If I go back, I have to reset here. If I change the input voltage, and I think I can get to the value that actually it sees high voltage. Let's see, my battery, I've put it 60 volts. That should be 3 seconds. If in 3 seconds it doesn't come on, it means high voltage level is not reached here. I can increase that volt, but I'm sure the low voltage I can get here. You see, the buzzer is now running, and in that state, when it's flickering this LED and that LED, it means you are out of the maximum power voltage of the module. Now it has already actually gone into error mode, like alarm mode here. So it goes into alarm mode, and that mode you can't come out until you reset it and restart. Okay, and still the alarm is still there, it won't come back you have to reset it. And the alarm is still there, so the voltage is way below, somewhere there. I was way below. Okay, right, now I've actually reset it and it goes into off position. That's the normal position. I put it on again, starts to run. It's running now. Remember, that side is happening, and I'll show you. Right, and then now it has come on. Right, now I can go down here so that you see how the LEDs behave, slowly going down, which using this port is actually right now it's in off the maximum power point voltage of the module. It will go there in that stage, and then later on it will go, after 3 seconds it will go into alarm mode. I think somewhere below there it will switch to alarm mode because they've gone below 30 volts by design. That I fixed it. So I've not reached, I've reached. Okay, so that's alarm mode. There, when it gets into that, it is off, and you have to reset it using this button and then switch it on there. Right, let's see if it is in the battery mode. The battery mode is this one. Okay, okay, voltage must be right for the inverter to start, for the inverter to be reset. You can't reset when the battery, the supply voltage is out. Okay, so let's change to battery mode. It's low. Now it's in battery mode. So in battery mode, the voltage levels here are different. So when I start it in battery mode, you see the LEDs, they just go on. Okay, they are flickering, but it's only that the LEDs will run at a higher frequency, on off, because they are solid on. They are actually solid on. These LEDs are solid on to the eye, but behind is actually on off very fast. And the same still happens here. The same still happens. It actually will switch on this one, and then the next, and then we'll start running. Okay, so did I switch it on? No. Okay, I must switch it on. Okay, switch on. It's now running. Same signals output, but here LEDs, they don't change. They just show you the level of the supply of the battery. Actually, these LEDs are just showing the level of the batteries, but the error signals are still the same. These two flickering, showing you the battery is now getting lower, and the bars are coming on, and then it comes on for some time and then goes off. And then if these two are flickering alternatively, it means there is an error. The inverter will see shut down. Right, okay, that's for the battery side, similar to the module side. Okay, now I think on the 4013 setup, okay, I must explain that. You can see that output C and output D, there is that gap here. This gap here is actually the dead time, as I explained before. Channel B is in interface to channel C, as you can see here. When this one is high, the other one is low, just straight on like that. And these are the legs actually of the H bridge. This signal and that signal are actually the top or the bottom, whichever way you choose. One is top, the other one is the bottom MOSFET, and these two will actually be similar. When this one is high, the other one is low, and you choose which one is top, which one is bottom. But now if I add like this, you see that the signal behaves like this. This is the output signal that we want. But basically the trick is, when you feed in the signal like this, low pulses, when you have low pulses, you can actually control this pulse with this dead time. I've used the high pulses myself on the 4013, and it's working. The thing that is tricky there now is these 4 output lines: pin number 1, pin number 2, pin number 13, and pin number 12. When you are actually wiring it to the MOSFETs, when you do that, the high pulses, you have to, for the designs that are there on the net, it is low pulses, and pin number 1 and pin number 12 driving the high MOSFETs, pin number 2 and pin number 13 driving the low MOSFETs. You should actually be careful when you actually connect the outputs of these ones to the MOSFETs, because there's a point where you have the signal very much small, that maybe to a point where it is actually zero, no output at all, because the MOSFETs are not even driven at all. Let me just stop and show you what I mean. Okay, I remember we are actually inputting low pulses here. So when we are inputting low pulses, this is what comes out. Okay, we run, check channel A and channel B, right? I add channel A and channel B. You see, these are the signals that we want. Okay, right. But if I stop, okay, if I change around this here, we input high pulses. We are now inputting high pulses here. Okay, so what does that mean? We are saying here this one is coming direct, this one is coming as a high pulse. Okay, now let's run and see the difference. You will see the difference. See the signal that is coming out now when you add the channels. You see the signals that is coming out now. So this is what happens, the difference, what the difference will do. So this is what happens when you input the first latch there. When you input high pulses, this is what comes out. And then when you change around and input low pulses, and this one being high pulses, is the other signals that we were getting there. And this is actually, you can change this pulse width, and you can only change it by adjusting the pulse width that you change there, that you are inputting, how big are the high pulses. So adjusting the high pulses will adjust these pulses here. So that's the difference that makes whether you are inputting high pulses or you are inputting low pulses. And I hope you understand what I mean by high pulses and low pulses. It's coming from why there's small pulses. It's coming from the differences between these two. You see, there is only that small difference where the difference here is adding, whereas here the difference is subtracting. So you have a bigger zero there and a small high there, whereas the other side, the other time, it was the bigger adding part and the smaller zero. So that's the difference, and you should be careful when you're actually doing your pulsing here. Your pulsing is very critical here, whether you're inputting high pulses or you're inputting low pulses. Right. Here is a description of how you can get low pulses or high pulses, as I was describing, using the NE556 timer. Right, as I have explained previously on my video, my old videos on solar charge controller using the 555 timer, the inside working of the 555 timer is basically comparators and latches. Right, the first 555 timer, which is of course one IC, the dual 555 timer IC, the NE556. The first one is basically an unstable multivibrator. I think the literature is there on the internet. It gives you low pulses at 100 Hz, which means you just have output pin number 5 just going low for a very short time, and is fed to the next 555 timer, which is part of the same IC, or you can actually have them separate as two ICs, no problem with that. But it's fed to the reset pin and the trigger pin. When we have a low on the trigger pin and a low on the reset pin, it means a low on the reset pin. It means the output of this timer is high, meaning pin number 9 becomes high, and a trigger pulse, which means a low on the trigger pulse, the output is triggered to high, meaning pin number 9 is high, and it stays high as long as the timing of that 555 IC is designed to, because this 555 timer is a monostable setup. This is an unstable and this is a monostable, so the frequency is actually set up by this resistor and this capacitor. The other components are just for control purposes and maybe just to stabilize it, but otherwise here is the frequency, 100 Hz output on pin number 5 with low pulses. Right, I think on the previous explanation I actually showed you what I mean by low pulses or high pulses. So this is actually triggered to become a high, but this high is actually controlled by the timing of the threshold pin and the discharge pin, pin number 12 and pin number 13. A high here in a monostable state will depend on the voltage on this pin. So we are actually having this capacitor here on the threshold. Remember, the discharge pin, when this becomes high, the transistor on the discharge pin is turned off, and the threshold, which is actually an input, is now comparing, because it's just a comparator. So this is off. This capacitor C17 starts to charge, because this one is off now. It starts to charge to a voltage which is now, if it reaches 2/3 of the supply, 2/3 of the supply, remember this is our 15 volts, so 2/3 of 15 volts will be 10 volts. If it reaches 10 volts, this timer is actually well, it reverts back to a low on the output. Basically it has reached the threshold, so it goes low on pin number 9. When it goes low, it discharges the capacitor, C17, meaning that the discharge pin is gone low. That transistor turns on and goes low, so pin number 9 becomes low. So by controlling how long this high pulse is, you're actually controlling the pulse to the 4013 here, which is input here through here. This is an inverter, so you have low pulses coming here, and high pulses on the other side, because this is an inverter. You can use a transistor if you want for inverting. Most designs have got a transistor there. So this design is actually using well, on my design this is actually using high pulses. It's because I've fixed this charging time to be very short. Actually, charges in very short time, charges quickly. That capacitor charges quickly, so the high pulse is there for a short time, so you have high pulses there. So my design is having high pulses rather than low pulses. But if this capacitor charges slowly, it will charge maybe as slower to the point where the next pulse from the oscillator comes and it resets it, or it charges to a point where the pulse is long enough to become you have low pulses going into the 4013. So normally what you find on the designs on the net is that this pin number 13 and 12 actually they are not connected to this supply rail. They are connected to the high voltage pin output here, the high voltage output here, capacitor C3 here. They are connected here rather than connecting to the supply voltage in mega ohms. Sometimes 1 mega ohm, 2 mega ohms, depending on the time that you want, depending on the how long the pulse you want there. So it actually controls the shape of the signal that is going to drive these MOSFETs. That also determines how you connect these four outputs here. And remember, pin number 1 and pin number 2 are always in alternate. This is a D-latch. Pin number 13 and pin number 12 are always alternate. So as I have explained, usually most designs, pin number 1 and 12 are actually connected to the high MOSFETs, or vice versa. You can choose to have pin number 2 or pin number 13 connected to high MOSFETs. It still work, but this is one leg of the H bridge and the other leg of the H bridge, top bottom, or vice versa, whichever way you choose. But how you connect them now between this output and that output is determined by here, whether you are inputting high pulses or low pulses. For my design, I think this is evident, but most designs pin number 2 and pin number 13 connected to the high MOSFETs. So I think that's basically what is happening with this circuit here. It's simple but very tricky. When your signal here, you must know actually what you are doing there, so that you determine how you are going to connect these ones. But obviously what is rule here is these two are actually alternate, and those ones are alternate, meaning that that one is high and that one is low, and when this one is low, this one is high, and when this one is high, this one is low. Same with this one. Here the dotted lines are there. They're actually there if you zoom, just to say it's optional whether you choose the microcontroller way or you choose the 555 timer. When you choose the microcontroller, remove this timer. When you choose the timer, just leave out this one not connected to this point here. Thank you.